So this is the Mod 1 test from Chapter 1. Alright, limit as x approaches -1 from the right. So start with the direct substitution, and that would give you 1 minus 2 plus 1 all over 1 minus 1. So you get indeterminate form of 0 over 0. So we can factor this expression. The numerator factors to x plus 1 times x plus 1. The denominator is the difference of perfect squares. Cancel out the factors and then make a resubstitution of -1. So 0 over -2, so the limit's 0. The only time a one-sided limit is positive or negative infinity is if direct substitution gives you number over 0. Okay, number 2, when we make a direct substitution of 3, 9 minus 6, all over 27 minus 27. So this gives us a number over 0. Therefore, the one-sided limit will be positive or negative infinity because a vertical asymptote exists at x is equal to 3. So choosing a number to the left of 3, say 2.9. 2.9 squared minus 2 times 2.9 will give you a positive value. 2.9 cubed minus 27 would give you a negative value. So the limit approaches negative infinity. Alright, number 3 was asking for various limits. So given this piecewise function, the first limit as x approaches 1 from the left-hand side. So looking at the piecewise, that would be the negative x squared plus 2. Making a direct substitution, the limit is positive 1. The limit as x approaches 1 from the right-hand side, you would plug 1 into the x squared function and get a value of 1. Then for part C, what's the limit as x approaches 1 of the function? That would be equal to 1 because the one-sided limits are equal. Limit as x approaches 2 from the left-hand side, you would plug into the x squared function and get a value of 4. Limit as x approaches 2 from the right-hand side, that's the line, y is equal to 3, so the limit is 3. Because the one-sided limits are different, the limit as x approaches 2 does not exist. Alright, number 4, limit as x approaches 4 from the right. Direct substitution gives you 0 over 0, indeterminate form. So the limit as x approaches 4 from the right-hand side. If you chose a number bigger than 4, any value bigger than 4, if I plugged it into the numerator, 4 minus 5 would give me -1. So the absolute value takes the opposite of what's inside the function. When I divide that by x minus 4, now these factors, 4 minus x and x minus 4, are opposite of each other. They cancel to -1. So the opposite of -1 would give me a limit of +1. Number 5, limit as x approaches 0. Direct substitution would give us 0 over 0. So notice in the numerator, you can factor out an x from the numerator. Leaves you with cosine x minus 1 all over x squared. Direct substitution would still give you 0 over 0. So an x cancels in the numerator and denominator. And then this is your special trig limit. And that's equal to 0. So we had proved that in class. So that's one that you need to know. Number 6, direct substitution, again would give us 0 over 0. So notice we have a fraction within a fraction. So I'm going to keep the x in the denominator. In the numerator, what's my common denominator? 3 times 3 plus x. So the first fraction will have to be multiplied by 3 over 3. And then the second fraction will have to multiply by 3 over 3 plus x. Okay, so limit as x approaches 0. Distributing the negative in the numerator. Dividing by x is the same as multiplying by 1 over x. Combining like terms, we get negative x all over 3 times 3 plus x times the x again. Now these x's cancel, and we're left with the limit as x approaches 0 of negative 1 over 3 times 3 plus x. Substituting in 0 for x, we got our limit of negative 1/9. Alright, number 7, this should look familiar now as the definition of derivative. Direct substitution would give you 0 over 0. So distribute the 2. Square the binomial. First term squared, double the product, plus the last term squared. Distribute the negative to the last factor. All divided by delta x. Limit as delta x approaches 0. Distribute the negative into the middle factor. Okay, now crossing out the terms, 2x minus 2x, x squared minus x squared. Each remaining term in the numerator has a delta x, so we can factor that out. Now we've canceled the delta x's on the top and bottom. We get the limit as delta x approaches 0 of 2 minus 2x minus delta x. So making a direct substitution of 0 for delta x, we get 2 minus 2x is the limit. And then again in chapter 2, we know that this is the derivative. Number 8, find all values of c such that the function is continuous for the real number line. Okay, so continuity at a point. Function exists. Limit exists. And the last condition, those y values are the same number. Okay, so the limit as x approaches c from the left-hand side would be the quadratic. Replacing x with c, we get this function. Limit as x approaches c from the right-hand side would be the line. So substituting in c for x. Now in order for the limit to exist, we know that those two limits need to be equal. The function's quadratic, so solving a quadratic, we're going to factor this. I'm going to move the terms to the right-hand side to keep the squared term positive. This is a perfect square trinomial. So solving for c, so 2/3. Again, factoring this. First term squared, 9c squared, double the product, and then square the last term. Take the square root of both sides and solve for c. Alright, number 9, sketch this function. Identify x and y intercepts, vertical asymptotes, horizontal asymptotes, if they exist. Alright, an x-intercept occurs when y is equal to 0. Y-intercept occurs when x is equal to 0. So in a rational function, to find the x-intercept, all we need to do is set the numerator to 0. So we get negative 1/2, comma 0. For the y-intercept, set x equal to 0, so f of 0 equals 1 over the square root of 4, which would be 1/2. Vertical asymptotes occur where the denominator is 0. Number over 0 would give us those. So if we attempted to solve this equation, x squared can never equal -4, so there's no vertical asymptotes on the graph of this function. Horizontal asymptotes are limits at infinity. Remember, when you have a radical, that's the case when the positive and negative infinity will give you different values. Using our shortcut, I would have 2x over x. As x approaches negative infinity, my highest power in the numerator is 2x. In the denominator, that's where we use the definition of the absolute value. So it equals -2. Therefore, we have horizontal asymptotes at y is equal to 2 and y is equal to -2. Okay, so putting all this together, be a little tight to graph it. 2 and -2. As x approaches positive infinity, our horizontal asymptote is at 2. As x approaches negative infinity, our horizontal asymptote is at -2. Our x-intercept is at -1/2, 0. Our y-intercept is at 0, 1/2. No vertical asymptotes, so the domain is all real numbers. And then just connecting. Okay, lastly, now sketch this one. X-intercepts, set the numerator equal to 0, so x is equal to -7. Y-intercepts, replace x with 0, we get -7 over 6. So for graphing purposes, that'll be a little bit to the left of -1, or below -1. And then -7, 0. Okay, vertical asymptotes occur when the denominator is 0. So when I factor the denominator, it factors to x plus 6, x minus 1. So x equals -6, x equals +1 will be our vertical asymptotes. And then horizontal asymptote, when we find the limit at infinity, either positive or negative infinity, the function is bottom heavy, so the limit's going to be 0. 1, 2, 3, 4, 5, 6, 7. At -6, we have a vertical asymptote. At 1, vertical asymptote. The x-axis is a horizontal asymptote. Now you can verify using one-sided limits. The limits around the horizontal or the vertical asymptotes will verify the positive and negative infinity behavior of the function.